Do you know that arrays in Python are completely different from what you see in conventional languages like C or Java? Most developers mix up Python lists with real arrays, but under the surface, Python executes two radically different memory management systems. Let us skip the surface level documentation and look directly at the raw allocation block. When you initialize a collection using Python's built-in array module, you must provide an explicit typecode character. For instance, the typecode lowercase I specifies a signed integer layout, allocating exactly 2 bytes per element on the heap. This forces Python to create a contiguous C-style memory buffer where data sits packed back-to-back in memory. Conversely, a standard Python list is not a true array at all. It is a fragmented array of variable pointers, where each index holds a memory pointer wrapped inside a heavy generic object. Because a Python array is a true contiguous block, modifying its size triggers explicit layout restructures. When you call the append method, Python attempts to expand the block inside the current memory page to pack the item cleanly at the trailing edge. However, if you invoke the insert method to place elements at arbitrary positions, the virtual machine faces an expensive linear time complexity challenge. It must physically shift every single subsequent element in the memory layer forward by 1 byte index slot to clear the targeted insertion window. Removing data follows a similar pattern. Running the remove method forces Python to scan the underlying storage linearly until it encounters a value match. If a match is located, the item is destroyed and trailing blocks are shifted backward to maintain contiguous integrity. If you want to avoid this search overhead, you can use the pop method, which performs a fast, constant time operation by dropping the last element from the tail without an index scan. Advanced software engineers exploit this contiguous nature to read bare machine states. By invoking the buffer_info method, Python exports a direct tuple revealing the exact hardware memory start address of the buffer, along with the current item length. Since the data sits aligned sequentially, calling the reverse method does not require slow element reconstruction. The virtual machine executes an in-place pointer walk, swapping raw bytes directly within the allocation block. Mastering these low-level memory structures is exactly what transforms high-level scripting into highly optimized back-end systems engineering. Turn these memory layouts into your core development strategy and subscribe to maximize your runtime understanding.